is Mr. Scott Manson, keynote speaker. He is a fellow engineer at Schweitzer Engineering Laboratories. Scott Manson received his M.S.E.E. from University of Wisconsin-Madison and his B.S.E.E. from Washington State University. Scott is a fellow engineer at SEL. Scott is a registered professional engineer in 6 states and holds 30 patents. So Scott, it is a great honor to have you as part of UND's workshop and appreciate your time. And the floor is yours for you to share your slides.
Okay, let's give it a go here. Can you hear me?
Yes.
Okay, let's see here.
You're trying to share your screen, right? Yeah.
I am. Is it showing up?
Yes, we're good. Thank you.
Okay, super. Well, looks like I'm your, shall I begin?
Yes, Scott. Yes, you can.
Okay, it looks like I'm your lunch entertainment, everybody. So let's start off with a little silly dad joke, an engineer dad joke. It was about, it was about 18 years ago now. A young man walked into my office and he didn't see what was, he said to me, he didn't see what was so exciting about those generator voltage regulators. I'm like, good golly, that's called a layup. AVRs are not only exciting, they're magnetizing. Okay, nerd joke. But it gets to the point is that when you take apart something as seemingly simple as a voltage regulator, what is it doing? It's doing something that eventually can be resolved down to Maxwell's equations. If you can't do that, then you can't progress ahead. So back to basics. It's the most important thing we all need to do in our daily life. And when it comes to back to basics, there's nothing more first principle than eliminating complexity. Let me see if I can get this to move ahead. There we go. When you look at complex systems, I'm going to provide a number of examples here of how we can decomplicate the mystery meat out there of our power and cybersecurity systems. When we look at this, we need to understand the cost of complexity. Okay, it takes a lot more labor to maintain a system that is complex, a lot more time to document, a lot more effort to update service bulletins, functional updates, firmware updates. Oh my good heavens, labor, money. So obsolescence of equipment, right? A complexity needs to be replaced sooner because it becomes obsolete sooner. You're going to take more, just a simple example. How many times have we sat in meetings to try to decipher a complex solution? How many hours of labor is that costing us as a society when we're so short-staffed already? So, and here we are in an industry where it's difficult to find qualified engineers that know the basics, that can do the job, and then they'll change their job every couple of years to move ahead. So complexity is a killer financially. Some industries have actually considered resiliency, and rightfully so, to take priority over their finances or their efficiency, the commercial side of the power industry. And I'll make an example. An example is the defense industry. And I don't know the year that this became the law, but there was a program put together called the Energy Conservation Investment Program. Words matter. They were trying to conserve energy to reduce costs. It's a cost-based program. ESIP. Well, after about 2 decades of runtime, engineers, operators, managers realized that wasn't what they meant. It's not what they needed. What they needed was resiliency. So they added an R. They called it Energy Resiliency and Conservation Investment Program. So right there in our leadership, they addressed the issue as best they could with the limited knowledge they have. Let's make it an R. Let's make it a resiliency. So now it's called ERSIP. And today, now 2023, just a couple of months ago, I saw a request for quotation and a design package, and I read, and I quote, it said, "This microgrid project is a resiliency project, and it does not require a return on investment." Wow. Okay, wow, that's a huge statement, right? So it's important. It's more important than the money for some people. Okay. Um, so what is it that we need to do to build resilient systems in a simple way? Let's start by looking at some examples. Here you see on the left a ball valve governor right out of a patent circa 1860 in operation today. Many of these still are operating machines. In fact, on every mechanically fuel injected diesel engines for the last 80 years, there's one of these down on the speed regulator, on the fuel valve governor as an override. So these things in various formations still exist today. That's a long-lasting design. Look at that's over 100 years. It's over 140, 60, 70, 80 years. Wow, that's a long go, right? And it's going to be here for all of our lifetimes. But now look on the right-hand side. Here's a relatively new innovation. It's called a digital isochronous load share controller. When you tear it apart, you have machines that are regulated engines, regulated by the EPA, having a fixed controller that can only take speed over a CAN bus line to some auxiliary controller that communicates to other machines by CAN bus. That's an isochronous load share. That's complexity. Now, where does it fit in the whole big picture? If you zoom ahead, you can see, okay, well, there it is. Inside a Purdue diagram, it's that little tiny block on the bottom right. Generator, governor, controllers. Okay, wait a second. We've added a whole lot of complexity onto something that can also be done by weights and springs. And so, wait a second. Is the tail wagging the dog here? And are we going in the right direction? You got to ask yourself, is all that complexity necessary? Most cases, not. You do not need it. Uh, and here's a wonderful example. A couple years back, we converted a protective relay, the 700G, and we modified we just programmed it just right off the shelf to act as a generator controller. And then we realized, we can do that to control inverters. We can control Teslas. We can control all manner of battery control systems. Wait a second, but we need a plan B, because wait a minute, what if somebody corrupts our network? All that complexity above the governor control. Oh, there's an easy answer for that. It's called local mode. In this local mode, all communication is severed. But then how does it work? Well, it goes back to a model of quite literally a ball valve governor model. So having a plan B, that simple. Okay, love it. Here's another example. Circa Bell Laboratories, mid-60s, I'm not sure the date exactly, but we started seeing UART, Universal Asynchronous Read Transmit Device, basically serial communication. Okay, digitization of data, well, of information. Okay, and by about 13 years ago now, we had things called firewalls and routers managing Ethernet traffic. They were built for the office space, they were built not to be necessarily deterministic, nor necessarily very fast, but they were built for convenience, so to allow communication by default. Okay, and the method of network reconfiguration was something called rapid spanning tree protocol, or a derivative of it, spanning tree protocol, or any of the other proprietary versions of that. Healing time at its best was milliseconds, and if you see big networks with RSTP, sometimes the fastest you can converge them is in minutes, because they have such a large MAC table. They were built for internet technology offices. Well, that doesn't work in a substation. So about 2020, this company I happen to know pretty well, put together and perfected something called OT, software defined network. This is underlayment SDN, not overlayment. It is deterministic. It denies all traffic by default unless you program it as an engineer. It is configured rather than learned. That's cool. Nobody can teach it unless you do. And then it is microsecond network healing without a packet loss. It is specifically designed for operational technology space, for that location where speed is critical. That is a simplification. We went from very simple 1965 to very complex 2010 to now very, again, headed towards simplicity in 2020. Here's another example. Inverters, okay, they're on every nearly every renewable resource, not every, but nearly every, converting DC to AC and vice versa. Some of the features mandated in these inverters today are things like anti-islanding, also called unintentional island detection. Unfortunately, there's a dark side to advanced features. And one of the common outcomes, as I heard Brian mention this, you're going to have unnecessary shutdowns. These inverters are a little trip happy. Okay. Another feature is something called virtual inertia. We'll hit on that in the next slide a little further. It's known to create oscillations in a power system. These are not resilient. Okay. Cessation, again, how many times have we heard of a NERC report that says when an inverter suddenly shuts off on its own? Well, oh, wait a minute. That's not predictable. Why did that shut off? Because we need that power. It shouldn't have shut off. It's okay to shut off if it absolutely had to, but how many times have we discovered that inverters are just shutting off and there's no good reason? Okay, unpredictability is fragile. Okay, so cascaded controls, and that's a whole big bucket of Parks and Clark's transforms and a lot of complexity. How much of that complexity is causing these subsynchronous control interactions, these oscillations between wind and photovoltaic and generator voltage regulators, et cetera. So complexity in the inverter is eroding reliability. Let's go to simple here. Here's an example a little further. Virtual inertia. I like to pick on this one because I've been burned a few times, okay? So here you see a pretty traditional, this is a pulse width modulated grid forming with droop inverter overview. What you see here is they control the angular rotation and for power, and they control one of the axes for voltage and bars, and the other they try to squelch it to try to keep it so it's not an overconstrained power system. That's all the black part of the figure. And the red is the part we're going to talk about. That's the part where they tag in a virtual inertia. You've heard a lot of press about this as something that's helpful. Well, it's not what I've seen. And let's explain why. Okay, let's tear it down. So here, the way this works, the device has to measure frequency by measuring the zero crossings of the voltage waveform. And then it has to take a derivative. And then it has to inject it into an angle. Okay, got any problems with that? I do. Okay, first of all, what about during a fault? The voltage may not be there. That's a problem. What about during switching transients when phase angles can shift? Speed of light shifts in phase angles when there's an impedance change. That's a problem. So tracking frequency is hard. And you can tell the nature of how hard it is by just going out and looking on the internet to see how many frequency tracking patents exist today. So it's hard, it's not reliable, and the outcome commonly looks like this. This is a scatter plot. It should be a clean droop line between power and the vertical axis is frequency. The ordinance or the units are cut off, but it should be a smooth line. It's not. And why is it not smooth? It's because this virtual inertia term on this real inverter that was really installed and put into service, it was having it had a great deal of trouble measuring the frequency, and it was creating disturbances. Here again, complexities creating a problem. Here's another example of a complex problem. In this case, there is a relatively simple solution. When you energize a power system, it's commonly called black starting. What you do is there's a little bit of flux remnants left inside your transformers, and you end up having to punch through not only magnetizing your equipment, which is a big bunch of inrush, and it can be highly asymmetrical currents. In addition to that, you're having to energize loads. We call that cold load pickup. And that cold load could be anything from getting motors to start spinning to charging DC buses on big UPSs. Okay, it's a surge of power that needs to be served so that you can bring your power system up. Well, you can't bring a power system all up at once because that's a lot. Magnetization, out of phase current, real power, in phase current. And so how do you do it? Well, a great number of engineers have built very complex black starting algorithms with central controllers and communication, everything from satellite communication to millions and millions of dollars to put one of those in service. Or we'll call it the paperclip solution. You go out to your reclosers, you go out to your breakers, there's a relay protecting it anyways, and you put in an under voltage and a timer. That's a very effective way to re-energize a power system. I'll call that simplicity. That's what we're looking for. In a world of complexity, where we don't have synchronous machines, where we don't have the inertia of yesterday, let's use the intelligence on our power system to simplify something here like black starting. Okay, the ultimate in resiliency, I'm going to say is like the infinite Pez dispenser of energy, right? As much as you want, whenever you want. And at the speed of light. Wouldn't that be awesome? Well, actually, it turns out it exists. So take a look at this plot. This is a simple plot of a 100 megawatt turbine genset feeding into a load of around 92 megawatts. And they have a load step to about 97 megawatts. Okay. And what you see is the red line, the electrical power, is relatively instant. It instantly dispenses energy. Cool. We found the dispenser we're looking for. But the system slows down. Why? Because the fuel valve or the engine control system for that turbine takes time. That's the line in blue. The error or the integrated difference between the red and the blue, that's kinetic energy. That's why we have a speed loss. Okay. And so it exists. That's what we're looking for. That's the kind of simple solution we're looking for. Here's another example. We received a genset, a 60 kilowatt tactical quiet generator. And the first thing I like to do is fillet things out. So we filleted it out, laid it on the floor. How does this thing work? Put it back together. Eventually got it working again. And we found all this stuff. Like, wait, what is this? This is a Windows computer in a box with a bunch of boards. Oh my gosh, what a rat's nest. So we tore it out and we replaced it with a relay. Again, complexity reset. Simple, simple, simple. You have to, because it is all about reliability and it is resiliency. Here's another item I'd like to point out. Let's examine our assumptions about engine and generator control for a moment. I've heard at least two speakers mention an artifact called droop. Okay, so droop is the green line on this hand sketch, and that green line is where in the x-axis is power out of a machine, the vertical axis is speed, or synonymous with frequency since it's a synchronous machine. If in fact you have a droop line, the way this works is that as the speed drops by the previous figure, as the speed drops, power goes up. That's actually makes sense, right? You're going up, you're driving down the road, you hit a hill, you slow down. Oh, I applied the gas pedal. Good. I want to go bring my power up. That's the way it's an intuitive, inertial based concept. However, let's challenge that. Let's play a little here. What if the line were as shown in the red? Okay, so wait. So now if we slow down, we take our foot off the gas. I mean, that might be like my grandma, but no, seriously, that's not the way we drive. It's not the way power system works. Okay, so but the truth of that red line is it's an instability. It's like taking your foot off the gas as you approach a hill and hitting the brake, right, and hitting the accelerator rather as you go down a hill. So that's instability. That is a region we'll call unstable. It's fun to tear these little, these I think long-standing notions apart a little bit. So if the red indicates an unstable region and the green is a stable, known, good droop line region, what's the blue? Oh, turns out that's called isochronous, constant speed. Wait a minute. It's like the cliffs of insanity, right? it's which side of this line are you on? Go just a little bit to the right, you got into the crazy land. Unstable, stable. Wait a minute. So in an era back 100 years ago, where ball valve governors, there was some slop. There was always some imperfection in everything built mechanically. If you tried to make an isochronous control system, what happened? You had instability for this very reason. And so why did they build drip lines? Well, to bring it into a stable region. So what really is a drip line then? It's positive feedback avoidance. Let that sink in for a minute. What it really is, when you tear apart the onion, get to the root of it. Okay, so let's just talk about positive and negative feedback. People like positive feedback. Yeah, we like that, but control systems don't. Control systems go completely unstable with positive feedback. Control systems and some engineers work best with negative feedback, right? This is the point. And so here's a classic assumption. Now, why do I bring this up? Because parallel islanded gensets from every manufacturer in the world work how? They work in isochronous. How come they work? Well, they don't play nice with others. They're become proprietary. And guess what? We've discovered they all sneak a little droop line into their controller. Okay, interesting point. Another point to make about simplification is that project execution is done by humans. Project execution by humans is prone to errors. We all make lots of mistakes. We need someone to check our work. Quality control is therefore mandatory in our trade. Now, how do we ensure that the outcome looks like we want it to be? We want resiliency. How do you do it? Well, there's some very fundamental basics that we need to observe. Number one, following a process creates consistency. Consistency allows us to measure something. If we're not consistent, we can't measure it. Once we measure something, we can improve. If we don't measure, we can't improve because we have no metric. Measurands don't exist. If we are improving, we can lead the way to quality. And quality is how we lead our power systems towards resiliency. Without quality and consistency, we're getting nowhere. And it starts not with technology, and I've learned this the hard way as well. It comes down to process. The most brilliant engineer will spin if they don't have a clear process to work on. That means even when we're doing things very inventive, we need to lay out a plan. That is essential that we all follow that paradigm. Now, here's a quote that I read many years ago as a child. Mark Twain was one of my favorite authors when I was a child, and he said something that sticks with me today. He said, "I don't have time to write a short letter, so I wrote a long one instead." Huh. What he's saying is it takes a lot of work to make things simple. Yeah. So it really is the brilliance of our trade is to reduce complexity. And the things that we must all be wary of. We must all be wary of things like, well, groupthink. Oh, they said it, so we believe it. That's called Me Too thinking. That's dangerous. Always be a skeptic, right? You know where that's gotten us in history, and it works in engineering just as badly. Making assumptions. You make an assumption, well, my father used to say, well, you can read what assumptions means. It's called, it means wasted time. Don't waste the time on an assumption. If you can't trace it to the physics and the mathematics you were taught, to the known laws of physics, then it isn't real. Straight up. And the one that we have to deal with, sadly, is the ultimate buzzkill, right? It's the politics. Not just the one in the newspaper, but the politics in the workplace. Those are buzzkills for innovation. We need to, avoid that complexity. Let's focus as engineers on solving problems. Commercialism, I think the way to put that is greed. Again, total buzzkill. And then timelines. Hard timelines exist and you have to follow them, but shortcuts ensue. So these are things that kill simplicity. And one of the plots I love to show is this. We used to call it the rule of three in programming, and it goes, and there's actually like entire methods and practices around coding that of a similar genre. The way I put it is this: in the first step of programming or invention, whatever you're building, you bravely or naively dive into solving a challenge. How hard could it be, right? Let's do it. Okay, that's fun. It's exciting. It's adventurous. Lots of learning, failing, and eventually you get there mostly, and you get it working. But it's usually at the end a gross design, and your code is spaghetti, and the hardware is, well, not optimal. Okay, you're here. You've started to make things very complex. That last 10% is sadly 90% of the work. And that last 10% means you redo your system top to bottom. That's phase two. That's called a redo. At this point, you've really hammered out how the control system or the algorithm or the protection or whatever you're doing relates to Maxwell's equations and other physical known laws of our universe that we're aware of. And you're getting some measure of clarity. And now you're starting to see through the fog and you realize, oh, good heavens, there's a simpler way. Usually you're out of time and you're out of budget and everybody's out of patience. But if you can knuckle down and really dig deep, you can do what's called a complexity reset. That means weekends and evenings because you're already out of money. It means doing it right a third time. And that is where that you've now, in a very simplest fashion, found the absolutely most elegant and simple way. And you've backed it all up with mathematics. You've backed it up with papers that are peer reviewed. You've backed it up and it's solid. It's repeatable. And that's what we're looking for. So I challenge all of you as you build your next generation of design, whatever it is, let's go out there and reset that complexity. That proves that you've gone that extra mile, that third step. And in that token, and I'm going to finish early, but this is okay. Have you ever stopped to ponder something as simple, something so mundane and so everyday as the paperclip? I bring this up because it's a great example of how we should really step back. If you've ever just type Google and say, ways of binding paper, you're going to find comb binding, ring binding, stitch binding, ring binding, case binding, every kind of binding you can imagine. But there is nothing more simple or elegant than a piece of wire twisted and slipped over a piece of paper. And that's the reason when I see someone who's actually paid the price personally to go to that extra mile to perform a complexity reset, they've done it. I'll give them a paperclip. Simplest, purest way of saying thank you for doing the right thing as an engineer. And with that, I'm done.
Thank you, Scott. I think appreciate for your insight. I think the paperclip sounds very nice. I think it makes sense. And okay, give me 1 second. We have some time to get some questions, so participants can field their questions on the chat or the Q&A. So we could ask Scott some questions. So let's see, while we wait for some question, and I mean, we have if something comes. How do you see resiliency
Hmm.
from cell
Yeah.
perspective, from your company's perspective.
Yeah. There's a lot of banter. It had become a popular buzzword. But let's just take a moment. Let's tear it down. Let's first of all, I won't answer the question directly. I'm going to answer it indirectly. Reliability is a known measurement. It's a metric, it's a measure, and it's something we measure. Say KFI, whatever they are. It's a measurement of your uptime, how much time your lights are on. Resiliency is the bit you're we're still looking for good measure ends, but uh, resiliency is the ability to take a punch and recover. A major load upset, a loss of a transmission line, a sudden loss of generation. Resiliency, we would love to have more measure ends. The simplest measure end I have for resiliency is keeping it within a reasonable voltage and frequency so that loads don't trip off on their own. Yeah, right. That region of stability, staying on the target, that to me is resiliency, and that's certainly what my customers consider it as well. At SEL, we provide power management, energy management, remedial action schemes, special protection schemes, microgrid controls, all invariably trying to keep the frequency and voltage within nominal so that loads stay online, and that is resiliency. You need high-speed data sampling um, directly from the devices measuring, and that's why we like C37118 right out of the relay, because the less mystery meat between you and your data, the better. So let's get it right from the device that measured it, and that's the relay. And we put that into a piece of software we call SynchroWave Operations to time synchronize the data and actually get something of a picture of our resiliency of our power system. I frankly, I feel like I'm running blind. When I'm looking at a power system, if I don't have real-time data on voltage, frequency, power, reactive power, at a bare minimum, I'm running blind. And the sample rates we usually look at for those wide area systems are at the slowest 1 second, but now frequently down to 1 cycle. Every cycle, I'd like to see that data. And then when we see a defect, we like to dive into the higher sample rates of the event reporting, the oscillography, right out of the electronics, and go look at exactly what the relay saw. So I know I'm meandering here, but resiliency is about taking a punch and proving it. Whereas reliability is about, it's more of a financial issue. It's more about how long were your lights on and how long were your lights off, and is there going to be liability with that? That's the way I see it.
Thank you. I think that's appropriate. I think we have another question. In your discussions with electric utilities, do you see adaptations for more advanced modern relays? Whether it's for microgrid controls, do you see the return on investment value from with the smaller co-ops or smaller utilities? What are you reading? Are they adapting to new relays, or what are we missing, and for everybody to participate to have that good situation awareness that we want in the grid?
Well, thankfully, the power system fundamentals haven't ever changed since Edison and Mr. Nikolai Tesla, duked it out. They really haven't changed. The synchronous machine of 1910 is still the synchronous machine of today, with just a few changes in materials and shapes. So thankfully, those electronics that were designed so well in the 80s and 90s still work today. And we've been very successful at building more and more complex solutions with those same relays. The way that we utilize the data changes, though. So for example, we may have a relay that samples at 4 kilohertz. And it turns out in most cases that's plenty fast enough. But what we need is algorithms that are more advanced. And so what we do is we take real-time data sets off the relay and we send them over protocols like, Goose, C37 and others, and we send them to a central processing brain, a programmable controller. We call it a programmable automation controller, an RTAC, real-time automation controller. And we send it there and we build libraries and we build algorithms to augment the relay. The relays, its job is to prevent catastrophic failure to your equipment, to the environment, and to humans, right? It's a protector, but it's also a really good data spy. It's excellent because it has its fingers on the current in the volt. It knows exactly what's happening. So we like to extract the data right out of the decision makers on the power system, which are the relays. And we use that for our bigger decision making. Now we use that for our microgrids or remedial action schemes. And then the neat thing is now that you've data consolidated it, now the data is already there and you can pass it up to SCADA. So when I see parallel systems with PLCs and RTUs and older designs, I think, well, first of all, you're looking at a different data set than the relay seeing. So how can you make a good decision? You have to make decisions based on the data that's coming through the decision makers, which are the relays. That's why our architecture is the way it is. And it's highly effective. It's proven well for all renewable microgrids with zero inertia, and it's proven to work well with traditional power systems. You have to be careful with your protection. You have to be very thoughtful and mindful of your designs. But largely, as long as we have real-time data sampling available to some controller, like a real-time automation controller is my favorite, why we can do everything we need to for a power system today, and I think for the rest of my career and beyond.
Great. Thank you again for the detailed answer. I
Yeah.
think we have this audience is largely students and faculty and some for industry. And from your own experience, and Cell is a leader on this relays, so what do you see, or what type of advice do you have for students and faculty? Or what do you see in terms of open-ended research gaps in protection relays, that you want to highlight that they may want to focus on?
Well, I tell you, I absolutely love the traveling wave phenomena and the research we've put into that. So if you want to look at something really interesting, go look at our traveling wave products. It samples at a higher rate than other relaying and uses different principles. It's, I think, especially pertinent when we're trying to get more out of a power system than ever before. Right? We have corridors where we're burdening them higher. We need to start anticipating events. And so when I see it, how do we anticipate a fault? Well, turns out when you sample faster, you start to see events, and you actually could start to see some little bit of buildup to what could soon be a fault. I think there's something really there, and that's where we should focus a lot of our work. Another great thing to look at is just back to the fundamentals, simplicity. A differential scheme, try to beat it. It's so easy to put together. And of course, we all struggle with the different type of inverters on the market. There's a lot of, unfortunately, misinformation about inverters. And part of it is just time, is that the leaders of many of our engineering groups didn't get a classical education on inverters, and they need it. Because guess what? Inverters can provide negative sequence. Guess what? Inverters can do what a generator does. It has limitations, but they aren't what's publicized. And I think that we should all take a moment to go really understand, go take a class from Brian or another professor to go figure out in your mind, till you understand how it is that the internal workings of an inverter can produce what we need as signature so that, protection, metering, and control can still work. And they can. Unfortunately, I think we're at a place where complexity has damaged and tarnished the image of the renewables initiatives. And yeah, we got the left foot ahead here. We stumbled over ourselves. We started into this whole trade of renewable energy and intermittent energy really without having really mature designs. And my advice is, let's simplify those inverters, make them as absolutely dumb and simple as we can, make them look just like a generator circa 1910. And if we can do that, we could get back on the rails, back on track with our agendas and our hopes and our dreams for what we could turn this power system into. But until we do that, we need to take a great big pause. This is a very dangerous place we're in now. unreliable inverters are affecting our resiliency and reliability. I mean, I could go on about that all day long.
Well said, Scott. Thank you, Scott, so much for your time today. I think you will send you a nice plaque for your time, and
Okay.
appreciate you for your contribution. So
My
thank you so
pleasure.